So in this lecture, we'll study chapter 2 of the textbook, which talks about various aspects of circuit elements. So we'll go through them one by one. The first one is linear and nonlinear circuit elements. A linear circuit element is one whose IV relationship is linear. And by IV, I mean current voltage. So I will use this terminology. That I is current and V is voltage, and the mathematical relationship between the current and voltage is called the IV relationship. So for example, the resistor has V equal to Ri, so that's clearly a linear relationship, and so the resistor is a linear circuit element. On the other hand, a diode, I'm not sure you've seen this equation before, but the diode current can be written as some constant times exponential of the diode voltage divided by another constant called the thermal voltage minus 1. So the current varies exponentially with voltage, so obviously this is a nonlinear IV relationship, and therefore the diode is a nonlinear circuit element. Now, what about a relationship like this, I equal to some constant times V plus another constant? Is this linear or non-linear? It seems to be linear, but we'll see in a minute. Let's look at a capacitor. So you are familiar with the fact that for a capacitor, one can write Q is equal to CV. Charge is C times voltage. We want to find the current voltage relationship of the capacitor, and current is of course the rate of change of charge with time. So I is dq dt, so we differentiate this, so we get C dV dt. So I is equal to C dV dt. Is this a linear relationship or non-linear? Slightly unclear, we shall see. Last lecture we saw that if we have this circuit, a simple RC circuit with a constant voltage source, then the current in this circuit as a function of time can be written as the constant V0 by R exponential minus T by RC. We may be tempted to conclude from this that the capacitor is a nonlinear element, but we'll see. So in order to determine if any circuit element is linear or not, we need a definition, a mathematical definition of linearity. So here is a definition of linearity. So let us say we have some circuit element across which a voltage V exists and through which a current I flows, and in general the voltage and current are both functions of time. Now suppose if we apply a voltage V1 to this element, then a current I1 flows. And if we apply a voltage V2, then a current I2 flows. Then, if when we apply V1 plus V2, the current that flows is I1 plus I2. And if we apply a voltage K times V1, where K is some constant, and the current that flows is K times I1, then we say that the circuit element is linear. So if these two conditions are satisfied given this initial data, then we say the element is linear. If these are not satisfied, we say it is not linear. Alright, so let us apply this definition to our two cases of a circuit elements we were not sure of. So let's look at this I equal to GV plus I0, where G and I0 are constant. So we say if we apply a voltage V1 to this circuit element, then the current that will flow from this equation is GV1 plus I0. If we apply a voltage V2, then the current that flows is GV2 plus I0. Now if we apply V1 plus V2, then the current according to this equation is G into V1 plus V2 plus I0. So the question is this equal to I1 plus I2? If it is, the element is linear. If it is not, it is not linear. Similarly, if we apply a K times V1, then the current according to this equation is GKV1 plus I naught. Is this equal to K times I1? The answer, of course, is no for both of these. You can see that very easily. Therefore, we say that this element is actually not linear. Okay, let's look at the capacitor. So for the capacitor, we said the current voltage relationship is this equation, I is C dV dt. So if we apply a voltage V1, then the current I1 is C dV1 dt. I'm sorry, this is, let me just correct this. I1 and I2. Alright. So if we apply a voltage V1, then the current that flows is C dV1 dt. If we apply a V2, the current that flows is C dV2 dt. If we apply V1 plus V2, the current that flows from this equation is C into d V1 plus V2 dt. This. Is this equal to I1 plus I2? It is actually. Suppose we apply a KV1. So the current is C d KV1 dt. Is that equal to K times I1? It is. Therefore, the capacitor is in fact a linear circuit element. Another way of saying the same thing or arriving at the same conclusion is, I'm not sure if you've seen any differential equations before, but this is a differential equation. And this is a linear differential equation. And if the differential equation defining any circuit element is linear, then that element is linear. So the capacitance is a linear circuit element. If I must make a qualification, if the capacitance is a constant. There are devices for which the capacitance itself is not a constant, it is a function of voltage, then it is not a linear circuit element. We are talking about the parallel plate capacitor, which is a linear circuit element. Alright, let us look at another classification of circuit elements, active versus passive. Passive elements are elements that either dissipate or store and return power. Passive elements are elements that cannot supply power to a circuit. They do not supply energy. So a resistor, of course, only dissipates, just takes power from the circuit and dissipates it as heat. Capacitors and inductors take power from the circuit, they store it, and at a later time they return that power to the circuit. So these are both types of passive circuit elements. Active elements are, of course, elements that can supply power or they can transfer power. Sources, voltage sources, batteries supply power to the circuit, so they are called as active elements. Or elements that transfer power. So transistors, amplifiers transfer power. Let us look at an example of this to illustrate. So let us say, I'm not expecting you to really understand this well. We'll learn this after 3-4 weeks in some detail, but this is just to illustrate. So this is the symbol of an amplifier. So it has inputs and it has an output. And an amplifier is by definition an element whose output is an amplified version of the input. A is some constant, I have taken it as 200 here. So the input to this circuit is a voltage Vi, the output is Vo, and the relationship is this. Now if it is a very good amplifier, then the current drawn by the amplifier from the input voltage source is 0. So if the input current is 0, then the power supplied by the input voltage source, of course, is also 0 because it is Vi times Ii. So the input power is 0. Now an amplifier needs a DC power supply to operate. So you have to connect some battery or something to supply power to this amplifier. At the output, so we say the output is equal to a Vi, and I'm saying let that be 200 Vi. And let us say at the output we've connected a speaker. So let us think of input as some small audio signal or voice signal or something that is coming from the microphone, and the microphone output is very small, it is like a few millivolts, and this amplifier amplifies it so it becomes volts, and we are using this to drive a speaker, and our speaker will have a much louder volume than what the microphone can provide. And so we've connected a speaker, and let's assume that the speaker can be represented as a simple resistance of 10 ohms. Speakers are usually actually 8 ohms, but 10 simply makes the calculation easier. So we say 10 ohms. And so now let's say we have some audio input coming in, it is getting amplified, and the speaker is being delivered power. How much is the power delivered to the speaker? It is, if we represent it as a resistor, then it is VO squared by RL. You know that. So the output power is equal to VO squared by RL. VO is 200 VI. So this is 200 squared times VI squared by RL. So 40,000 by 10. So 4,000 VI squared. So if VI is some small number, we get some finite output with zero input. So this circuit is amplifying a signal, but it is not taking any power from the signal, but it is generating an output power for that signal. It is actually taking power from this 5-volt battery. So this is called as transferring of power. It is taking a 5-volt power to amplify this signal and create an output that is a high power audio signal. So therefore this amplifier is called an active circuit element. Alright, let us see. Now let's look at what are called as the well, I want to plot the IV characteristics of various circuit elements. This is a very interesting exercise. So let us start with the resistor, of course, which is trivial. So typically when one plots IV characteristics, one plots the current on the y-axis and the voltage on the x-axis. For a resistor, of course, I is V by R. So we'll get a straight line passing through the origin, and the slope of the IV characteristic is 1 by R. Now let's look at a voltage source. We want to look at the IV characteristic of a voltage source. So first of all, these are two symbols. I'm sure you've seen these. So this is a symbol for a DC voltage source. Let's say I have a value of 1.5 volts and some current I is flowing through it. And this is a symbol for a generic voltage source, which can be DC, AC, transient, something. So Vs is the name I have given. So it could be a sinusoidal source. It could be what is called as a unit step, which we'll see later. It can be triangle, whatever. So this is a generic symbol for a voltage source. The question we are asking is, if I want to plot the current versus voltage relationship for a voltage source, what would it look like? And in other words, how does the current on the y-axis vary as a function of V on the x-axis? So the fundamental thing we recognize about a voltage source is that the voltage across a voltage source is always constant, independent of the current through it. The current through a voltage source can be anything. The voltage is always constant. So for example, for this 1.5 volt, the voltage is always 1.5 volt, independent of the current. Here, the voltage is always Vs, independent of the current. So what is the IV plot of an element whose x value is always constant? What is it? So let's see. It is a vertical straight line. So the voltage across the voltage source is always Vs, independent of the current through it. So the current can be positive, negative, large, small, zero. The voltage is always Vs. Now let us make this a little complicated. So let us think about this. Let us say I have this 1.5 volt battery and I connect a 0.15 ohm resistor across it. Then the current in this circuit will be 1.5 by 0.15, so 10 amperes will flow. Now suppose instead of a resistor I short circuit the battery. How much current will flow in this circuit? That is the question. So there are two answers. If this voltage source is ideal, then what will happen? The current in this circuit is 1.5 volt divided by a zero resistance, because short circuit is zero resistance. So I is equal to 1.5 by 0. So an infinite current will flow. So if the voltage source is ideal, which of course it never is, then an infinite current will flow. But of course, sources are real. So what will a real voltage source do? What will it do? Some finite current will flow, and it will flow as long as the voltage source and battery in this case has stored energy. Once all the energy is dissipated, current will stop flowing when the battery becomes fully discharged, which of course will happen very quickly. Okay, so now we want to represent this phenomenon that when a real voltage source is short circuited, a finite current flows, not an infinite current. Okay, so let us suppose that this battery can supply a maximum of 7.5 amperes, just some value. So when I short circuit a battery like this, the current that will flow is 7.5 amperes. So I want to represent this in an equivalent circuit. So what do I do? Again, I think you know the answer, so I'm just showing you the answer. So what we do is we put a resistor in series with the voltage source to represent the fact that it is not ideal. So that now when we short circuit this, the current will not be infinite, it will be Vs divided by this value. So if the voltage is 1.5 volts, 1.5 by 0.2 is 7.5 amperes, so the maximum current is 7.5 amperes. So real voltage source is represented by an ideal voltage source in series with a resistance. Incidentally, I have written here, can you find? This is, so if you think of a 1.5 volt battery that you can go to a stationery shop and buy, I have not been able to find how much current this 1.5 volt battery can supply. And I'm saying not able to find from some source on the internet. So I'm asking if you can find out and let me know these batteries that one can buy in the stationery shop, chargeable, rechargeable, something, how much current they can supply, the maximum current they can supply. If you can find it, please let me know. Okay, so this is the same thing. So you have 1.5 volt, 0.2 ohms. Now what is the IV characteristic of this real voltage source? So the ideal was a vertical straight line. If we have a resistor in series, what is the IV characteristic? So you think about this. I am not going to spend time, but the IV characteristic will look like this solid line. This dotted line is the ideal source. The solid line is the characteristic of this non-ideal source. It has a slope, and the slope is 1 divided by 0.2 ohms. Alright, so let's think about this just for a minute. So what this is saying is that if the voltage across this voltage source is greater than Vs, 1.5 volts, then current will flow into the voltage source. So that is the positive side. The current will be positive and it will increase as the voltage increases. Now what is happening when the current is flowing into the voltage source? What does that mean? That means the voltage source is receiving energy from the rest of the circuit. So this would happen when, for example, we are charging a battery, charging any battery, then the voltage source will be receiving current, and then what this is telling us is that the voltage to be applied to this voltage source has to be greater than 1.5 volts, only then will it charge. And when the current is negative with this definition of the polarity, that time the voltage source is supplying power to the rest of the circuit. And when that happens, the voltage that appears across the battery is always smaller than 1.5 volts. Of course, the difference is small because this resistance is very small. Here I have exaggerated. This line will be actually very close to vertical because the slope is very small. All right. Okay, let's go to current sources. So you may or may not have seen current sources before, but a current source is a circuit element which maintains a constant current through itself, whatever may be connected to it. So if you were to plot the IV characteristic of current source, where this is the voltage across the current source, then it will be a horizontal straight line. The current in this element is always I0 independent of the voltage across it. The voltage across a current source can be anything. It can be 0, it can be positive, it can be negative. What does it depend on? It depends on whatever is connected to this current source. We don't know the voltage across a current source until we solve the circuit to which it is connected. This is, I must emphasize, this is the same as in a voltage source, we don't know the current. So this is in this plot, the voltage across a voltage source is Vs. The current in a voltage source, we don't know. It can be anything. It will depend on what we connect to that voltage source. Okay. What about real or non-ideal current sources? So let's do a little exercise. So let's say I have a 1 ampere current source and I've connected a resistor R across it, and we want to watch the voltage as R varies. 1 ampere source. So let's say we connect a 1 ohm resistance across a 1 amp source. The voltage across it will be 1 volt. Let's say the resistance is 50 ohms. 50 ohms times 1 ampere is 50 volts. Let's say the resistance is 1 kilo ohm. The voltage across it will be 1000 volts. So if we increase the resistance across the current source, the voltage across it keeps increasing. What if we open circuit the current source? What is an open circuit? Open circuit is an infinite resistance. So if we open circuit a current source, that means we have an infinite resistance connected across it. Then the voltage across that current source will be infinite. Of course, if the current source is ideal. This is similar to a current in a voltage source becoming infinite under short circuit conditions. So now, if you want to represent a real or a non-ideal current source, how shall we do? What will a non-ideal current source do? Even when it is open circuited, the voltage across it will not go to infinity. It will be finite. So the way we represent this is by connecting a resistance in parallel with the current source. So now these are the external terminals of the current source. So even if these are open circuited, the voltage across the current source is limited to Rs times 1. So Rs volts. It does not become infinite because now we have a non-ideal parallel resistance across the current source. In an ideal current source, this Rs will be infinite. Alright, let's see. Now, all these circuit elements, resistors, capacitors, inductors, voltage sources, these are physical circuit elements. You can go to a market and buy these and put them together and build circuits. There is another class of circuit elements which are called as abstractions. They are not real in the sense so you cannot physically go buy them, but they are used to represent physical phenomena that happen in circuits, specifically in fact in electronic circuits. So let's look at 3 examples of these representative elements. So we already saw an amplifier. So an amplifier generally has 2 inputs and 1 output, and the output can be written as some constant times the difference between the 2 inputs. So basically what we are saying is that this node voltage in the circuit depends on two other voltages somewhere else in the circuit. Alright, let's look at a bipolar transistor. You probably have seen a bipolar transistor. So let's say we have a current source connected to the base and the current source value is IB. Then you know that the collector current can be written as some constant beta times IB. Beta typically is 100 to 500. So we say that the collector current of the bipolar transistor is 200 times the base current. In other words, the current here in this branch of the circuit depends on a current somewhere else in the circuit. Alright, this is a third example. This is called a MOSFET, another type of transistor, which also has three terminals, gate, source and drain. And for a MOSFET, very kind of elementary mathematics is that if there is a voltage Vg applied to this terminal, then the current in this terminal is equal to some constant times Vg. So the current here depends on the voltage somewhere else. Now all these physical phenomena it is convenient to represent them by circuit elements. So we introduce a class of circuit elements called as dependent sources. So dependent sources are not real, they are abstractions that are used to represent these different effects. And the fundamental property of dependent sources is that the current or voltage at some point in the circuit is a function of current or voltage somewhere else in the circuit. So there are four types of dependent sources. There are two dependent voltage sources and there are two dependent current sources. A dependent voltage source, the value of the dependent voltage source can be dependent on a voltage somewhere else, then it's called a voltage controlled voltage source, or that value can depend on the current somewhere else, then it is called a current controlled voltage source. Or if you have a dependent current source, the value of that current source can depend on the voltage somewhere else. So we say this is a voltage controlled current source, or it can depend on a current somewhere else. Then we say it is a current controlled current source. And the short forms are VCVS for voltage controlled voltage source, CCVS for current controlled voltage source, and so on. We will get used to this as we do put them in circuits and solve circuits. Notice that for a voltage controlled voltage source, this value is a voltage. Alpha Vx is a voltage. So alpha is a dimensionless quantity. This Rix is a voltage. So R must have the dimensions of resistance. This is a current. GVy is a current. So G has to have a dimensions of conductance, 1 by resistance. And this is a current dependent on another current. So beta is a dimensionless quantity. All right. Okay, last. Suppose I want to plot the IV characteristics of a capacitor. We've seen resistor, we've seen voltage source, we've seen current source. What will be the plot of the current versus voltage of a capacitor? Let's think about it. If V is constant, so if the voltage across a capacitor is DC, then the current is 0. I think you know that. So this is a meaningless thing because a constant voltage gives us 0 current, and the current voltage plot will be simply a I equal to 0. It will be just 1 point on the IV characteristic. Now let us suppose that the voltage applied to a capacitor is a sinusoidal signal. Let us say Vm cos omega t. If this is a voltage, then the current in the capacitor will be the C times the d by dt of Vm cos omega t. So that will be I equal to, so we differentiate this, we'll get minus omega C Vm sin omega t. So this is V, this is I. So what is the mathematical relationship between V and I then? It's of course here. So we use the trigonometric identity. We know that sine squared omega t plus cos squared omega t is 1. So sine squared from here is I squared by omega squared c squared Vm squared, and cos squared is V squared by Vm squared. So we get this equation. So this relates I and V. What is this? If you were to plot this, what do we get? We get an ellipse. So the IV plot of a capacitor is basically nothing if the voltage is DC. It is an ellipse if the current and voltage are sinusoidal. Suppose the voltage was linearly increasing value, then the current will be a constant, and that will give us a different IV plot. So IV plots of capacitors cannot be drawn generally. They can be drawn only for specific types of currents and voltages flowing in the circuit element. Alright, so that finishes this chapter and this lecture.